and he is going to talk about cyclic cocycles in the spectral action.
Okay, so thank you. Should I click this away? Or do you Got it. Okay, so thanks. Also, thanks for the opportunity to give this talk. Maybe a little bit different from many of the talks yesterday, that I will have some analysis. And there will even be some physics. So that's my challenge, to expose you to some physics. But okay, I will be gentle and take it easy. But at least I will try to explain how cyclic cocycles come about in the spectral action and what that is. So here's my plan. So I first, as I said, I will give you a little bit of an idea of gauge theories, how they appear in the context of spectral triples or in non-commutative geometry. Then I would like to look at the gauge invariant, which is a spectral action. I'll also explain what it is. And for that, I want to focus on Taylor expansions in the perturbation. So that's, and we will find in that formula, in this expansion, that cyclic cocycles appear, which are used to kind of integrate very nice, we think, very nice forms. And then maybe if time allows, I will look at loop corrections. So this, all this work, I mean, about the Taylor expansion, about the loop corrections is joined with the Teun van Nuland. So maybe I said this before, but the van, like in German, it means that we're from some place. Nuland is indeed some village. Cyclic is actually Sulichem is also a village in the Netherlands. Of course, I'm not from there, but someone in mind.
Can I ask my question now?
Yes, you can ask.
Can you tell us about the loop corrections, please?
When they come, what do you mean?
Okay.
You want to start at the end? Oh. Okay, so spectral triples and gauge theory. So for me, I would start with so this data AHD. We've seen it already before. So there's a unital of star algebra, just to be kind of safe side, or it's somewhat easier. Then there's this self-adjoint operator D, like the Dirac operator. That's really what you want to think of. And they both act on a Hilbert space H. And there are some conditions like compact resolvent and commutators being bounded. And the way to think about this D, which is actually quite useful to keep in mind, is I wrote it there as well. It's this inverse fermion propagator. So it's like, and it is actually like this. So if you take a spin manifold and you have a Dirac operator on there, then its inverse is telling me how one propagates from one point to the other. So it's like a fermion, like an electron. It's propagating. The way it propagates is prescribed by this inverse of D. And so somehow we capture the geometry by looking at how particles propagate in space. And that's exactly what this D tells us for fermions. So that's something to keep in mind. And even this arrow will come back in the diagrams in the loop correction. So
sorry, what does bracket C mean at the top? Commutators.
this is it's this guy.
Oh yes, the reference.
So I didn't even bother to put a date, because actually, if you look back, I mean, the notion of spectral triple, I mean, it's already in the early 80s that it's there. So, and in fact, I think 1980, that paper on the non-commutative torus has that same kind of ingredients to work with. So that's the reference.
Yeah, okay.
Now, the idea about this is that in general, actually, one can use this package to introduce a distance function on the state space of, say, the C star algebra closure of this star algebra A. And this is the formula. So you take two states phi and psi, and the distance is like the supremum of what the values it can take, phi A and psi A. With the condition, of course, on A is that the first derivative essentially is not too large. So this is somehow like, it's maybe this picture I usually have in mind, is that you try to translate distance between 2 points X and Y into function space. And the way to do so is by taking function values So this would be f of x and f of y. In such a way that so you can actually translate into function space what that distance is, as long as this f has gradient smaller or equal to 1. Okay, so then you take maximum.
Sorry,
then you
what's
actually
a
find-
bar? On your slide, you've got A equals a bar.
The
What's
C's
a
are
bar?
closure of A. So
What's closure? Which is
C's.
Completion.
closure because they're bounded.
Closure, okay.
Completion.
So this A,
Oh,
script A,
In
acts
the
as
bounded
bounded
operators on the Hilbert space.
on the Hilbert space A.
Okay, so this is a closed subset of BH.
Closed
And you're
subset.
taking, okay, good.
And D is of course typically unbounded. In the specific case of a manifold, a spin manifold, where you have a Dirac operator, then you find that this distance that you compute like that via such a sketch, actually, if you work out the B fields for this, you find that you get back the Riemannian metric distance function between 2 points x and y from this formula. And then the x and y, of course, the kind of the pure states corresponding to evaluation in these points. So this is somehow kind of the way to approach geometry. And then I said, okay, there's
So in that example, A is L infinity of the manifold.
yeah, but C infinity would be a little bit.
But you said closure.
C of the manifold.
No, then it would be C of the manifold. It's a C star closure.
Oh, the C star, yeah, well, L infinity.
No,
The
no,
normal
no, I
closure.
think this is one closure.
So continuous functions on the manifold. Okay, good. Yeah, okay.
Yeah, very good.
Oh, so this is just the uniform norm.
Yeah.
Okay.
Okay, so as I said, gauge theories somehow appear naturally from these spectral triples. I mean, you can give you a prescription of how to get to a gauge theory from that set of data. However, since I'm aware of the fact that not many of you may be familiar with gauge invariance or gauge theories, let me put it into a little bit of a historical context. Because so Hermann Weyl had a paper in 1918, which is called Gravitation und Elektrizität, and he introduced this concept of Maßstab invariance, which is like your measuring device. That's what I would sort of. I mean, Maßstab is hard to translate. I don't know if
Scale.
yeah, scale, but
Yeah, it's kind of scale.
it's kind of scale. So, what would you say?
No, scale is correct.
But it's like the thing to use, right? The physical.
Then it's a gauge.
Can we?
Yeah,
go?
sure.
It's a gauge.
I mean,
That's the word
it has
gauge is. Yeah.
two meanings, but the main meaning is that scale.
Yeah.
I mean, the instrument,
Measuring
you would
device.
not know.
Yeah, I think that's what well.
Normally-
you might, but I'm not sure.
Or something.
Anyways, so later it was kind of translated to eigenvariance or gauge invariance. But what happened was this. So he looked at this transformation. So that's a scale, of course, is lambda. So lambda is a positive function on a manifold. So this is all, of course, on space-time or whatsoever. And then G is the metric, which you transform by a scale transformation.
A Pi factor.
Well, factor, of course. So this is what remains from that discussion. But the second part,
Right.
where you translate, V is a one form, and it's supposed to describe the electromagnetic field. Okay, so that's my V. It's just think about the one form. And what it does, he said, okay, let me take a transformation of that as well with this log lambda. And then he was able, under the assumption of invariance under this transformation, to get to both gravity and electricity. So,
It was missing an eye.
just wait a few lines, okay? Okay, so Einstein, he was very critical about this because he said, no, this is impossible. This cannot be right. So this hypothesis of this invariance under this transformation, in the sense I just wrote it, this cannot be right because it means that actually if you would look at an atom and it looked at its spectral lines, its absorption lines, then it really depends, the location depends on what the atom did, what the history is of the atom. And this cannot be right, of course. So then Weyl tried to kind of, so this is all in the same paper because it's an addendum to that paper. Weyl tried to kind of tried to rebuttal, but it wasn't really working. But of course, what was missing, and there comes in the eye, was quantum physics, because this was in the 1980s. So we had to wait like 10 years, and then someone else, some other people, London, yes. He
One of the two brothers, which one? Fritz London.
Yeah.
They were
So London, 1927. Yeah. So it was said that no, you should not look at scales, but phase invariance. So lambda should not be a positive function, but it should be of modulus 1. And so then, so scale was replaced by phase invariance. And what I would like to kind of stress here is that this is very close to the way I just tried to describe the way we think about geometry using a spectrum. Because, so you can even somehow revive some of this transformation of G, which is kind of a scale transformation, by looking at this phase in the same way, by acting on the operator D, which is kind of capturing for me my scale, my metric. And now I transform D in the same sense of while as U du star. So it's an invariant, it's spectrally invariant, for instance. So you just take a transformation, which is, well, and now I write U to be that phase, but of course I want to kind of generalize that in a moment. But this is kind of the idea that somehow you transform using these kind of.
By the way, Walter, I think Fock Vladimir Fock in Russia also.
Yeah, they're at the same
came
time.
across this
Yeah,
idea.
there were two. That's
Same-
what I said
at the same
too.
time.
Yeah, sure.
That's right.
Okay, but so that's all in the context of quantum physics. So it works very well in the context of Hilbert spaces and unbounded operators. We're very close to that. Okay, so that's somewhat the idea of I or gauge invariance. So let's see how this actually gets a little bit more precise. If you take this data AHD, so the first thing that one can associate to this set is a bunch of phases, essentially, a bunch of unitaries. And that's my gauge group. So this is this U of A, these are unitaries in A, and they act in the same way as I just wrote in the sense of while by conjugating D by U D U star. And then what you can actually do is you can write this as a perturbation, which is linear. So it's D plus U D U star. And so this formula here, of course, that's not too difficult to derive, but the point is that U D U star, this commutator, is bounded. So it's a bounded perturbation, self-joint of D. So in that sense, it acts on this self-joint operator. So then one would like an invariant. And the best one can actually do here is to take a spectral invariant, something that only depends on the spectrum. And then, in fact, if you require this to be, say, additive, and the thing you have to write down is the trace. Okay? The trace of some function of D, where this function f is such that this trace is well defined. So it's just a very general kind of prescription. This f is actually part of the input. So what you're doing is you're summing f of the eigenvalues lambda k of D. Now, these perturbations that I was talking about, these are like a U D U star. I would like to think about them as one forms. And so more generally, one can look at one forms, and that's actually the same V as what I was looking at, but then slightly more general. So you take a one form, this omega 1 D of A. This is like you take the commutator with D to be sort of acting as your derivation, not really differential, but it gives me a notion of one forms in this general setup. And it's my general expression for a one form, which will play a role throughout the whole talk, is V, which is this kind of sum, say finite sum of AJ, and then D commutator with BJ, where these elements are in the algebra. So everything is kind of prescribed by the starting data, which is this A, H, and D. And look at perturbations of D of that particular form. And of course, the first one, where the gauge group acts, is a special case. And actually, if you transform that new object, then you find that V transforms, and it's exactly as Weil was trying to capture in his with this log of lambda, except that this is more like a phase. And of course, this is non-abelian in an even more extreme sense. And that actually, while didn't live to, so he didn't live at the time where non-abelian gauge theories were introduced. Well, he did, but they never kind of communicated about this somehow. So it was a 1 year of overlap even with Young. When did he die? 55. It was 54, so it was Young and Mills. And they were at the same place. Like the overlap of a year, but somehow they didn't dare to.
So implicitly here, you're introducing the adjunction, the adjoint operation on one forms. So it looks almost as if we're going to be heading in the direction of something like dihedral homology, not cyclic homology. You're going to be paying attention to this involution, anti-involution.
You can do that, but it's that pretty.
I mean,
Is that where we're going? Or
No. V is just no.
but you're insisting it's self-adjoint. I
Yeah.
noticed the substance.
Yeah, but what we'll see is that
comes from an explicit involution on the.
Sure.
Yeah, but I will-
Dihedral is just a small decoration, which will not play a fundamental role.
Well, that's my question.
No, but you
opposed
see
to
this,
playing
the
fundamental-
cyclic cocycles appear, say, at a different level. It's much more at this trace of f of d that we'll find it. And V is used to integrate
Okay.
these concepts. You will see that in a minute. Okay, so first a little bit of background on that, on the spectral action and what it's used for, because I said I will expose you to some serious physics as well. So there are some assumptions, but that's not too important for this because I won't dwell more on this right here. But if AHD satisfies some assumptions, then actually one can, so it's about, for instance, the form of F should be suitable, so it should be a Laplace transform. The spectrum should be, the dimension spectrum should be simple, so that you have a nice expression like this. And I introduced the scale lambda to kind of control this at an asymptotic expansion. What you find is that there is these expansions of traces of d to the minus z. So these are like zeta functions. And I take residues at these poles. That's my dimension spectrum. And there's this single scale invariant part where I evaluate at 0. So that's the zeta of d. It's just a trace of d to the minus z, then extended complex plane, and then evaluated at 0. And f at 0 is just the function that I looked at the beginning. And this is somehow the starting point for many of these physical applications, because, for instance, what one can do is if one looks at a manifold, a Riemannian spin manifold M, in addition, one looks at not just functions on M with values in C, but functions with values in some finite dimensional algebra. Then one can actually derive very concretely using Heath kernel coefficients an expansion. This expansion just as above, one can compute these terms. And one finds, for instance, this R square root of G, which is known as the Einstein-Hilbert action or Lagrangian. So that's kind of responsible for the gravitational equations of motion. Whereas this other thing here, this trace of F mu, that's what we call the Young-Mills term. So there's these kind of ingredients coming out of this expansion, which you recognize as physical Lagrangians, describing particle physics. Yeah.
But the deformation of the Dirac operator that comes from a change of metric is not shifting it by a bounded amount.
No. So
So this
that's
doesn't
captured
fit.
in D.
Yeah, so this doesn't fit into the formalism that you
No, so
had in the
V would
previous
be the kind of
slides.
the bounded perturbation that would be the gauge.
So is there a way, I mean, is that going to be relevant that you didn't include it?
No, it's I actually, one could say I focus on the gauge sector,
Okay,
but
yeah,
it's very
okay.
strongly connected to the
Okay.
background. And there's phi squared, which is also, I mean, that's then the upshot is that in V, one does not only have these gauge fields, but one also gets the scalar fields in there. And that's kind of the additional kind of
It's
property. of
exactly
this,
the right symmetry breaking mechanism.
because it's essentially what you get is the Higgs mechanism out of this computation. So that's.
I mean, let me just add for Ezra that the Yukawa coupling matrix is the Dirac operator in the small space. So
Is DF, right? But I think it's a good point to also leave this and try to kind of get back to. I am going to talk about this for time, but let's look at the results, the more mathematical result about the scale invariant part, which are these zeta functions evaluated at 0. And so what I look at is I take zeta of d plus v, so the perturbed one, minus zeta of d at 0. And Shamsuddin and Kohn in 2006, under some assumption on the dimension, but for that, I like to kind of refer to the next talk, dimension means. It's about summability, of course. They find this formula where you find psi's and tau zeros, they're cochains, which you use to integrate these forms. And these A delta A, they're universal forms. So where A is the universal one for corresponding to this B that I had represented using the commutator. And so what you find is that, first of all, the forms that you find are very well known, because this A delta A plus 2/3 A to the third is a Chern-Simons form, CS3. And the other one, delta A plus A squared, so delta A plus A is like F, it's a curvature. It's F squared that you find. So also here you find the Yang-Mills type term. And they're integrated against psi, which is a cyclic cocycle, and tau 0, which is a Hochschild cocycle. Then what they also realized is that if you look at what happens if you take this cyclic cocycle psi, you pair it with the K1, then it's trivial. And this is related to gauge invariance of the underlying theory. Now, our goal is to do this, but for the spectral action as a whole. So not only the scale invariant part, also not doing an asymptotic expansion, just take it as it is and look at actually powers of V perturbation and see what you get. Okay, so let's get started with that. So that's about Taylor expansion of this spectral action. So about 10 years ago, I derived a formula which is like that. And this bracket, I mean, so I at least learned it from Ezra's paper, but I think you learned it from JLO, or you adopted that notation with brackets. It's quite convenient. So let's do that here as well, but they're not the same brackets, okay? So I will tell you what they are. So it's first of all, you just take like n derivatives of this left-hand side. It's trace of f plus d plus v, where v is this particular type of perturbation. Then you that's like a Gateau derivative or Fouché derivative. Then you find that you can indeed have expressions for them, and they're of this type, at least under some assumptions on n. So it's like I take a trace of these v's that I plug in. They're bounded operators, but I put in these resultants z minus d to the minus 1. And then I multiply with f prime at z and integrate in a contour over the spectrum of d. So circle this contour. And for that, I need some assumptions on f for that to work. It can be done in a much better framework, which was done almost immediately by Anna Skripka. And then later on, last few years, with my former PhD student, Teun van Nuland, together with Skripka and then together with me, we used multiple operator integrals to kind of really have sort of the best possible expression, because it's really powerful to use them for these kind of perturbations. Also, I won't go into the details on that. In fact, I would like to use that middle formula as a sort of the working kind of a case. So under these assumptions, in fact, this assumption would be that the support of f is compact or something like this. Right. So these brackets, they have two fundamental properties, and these are the only things that are crucial for the rest. So actually, you can even forget about these trace formulas. But the fact that it is coming from a trace, it gives me this kind of cyclic permutation in the first, this identity that holds. The second one, and that's very similar what one finds in JLO, for instance, except that there is different kind of commutators, is that if you multiply A with Vj, you compare it to what happens if you multiplied it before. So that's kind of crossing the comma. That's the only thing that happens here. But remember that the comma is this z minus d to the minus 1. That's this result. So that's the same up to this additional term. So you pay the price, and this is the right-hand side, which is 1 degree higher. So subtract with one more ingredient, where this is the commutator of d with a. And the reason why this is so is because crossing that comma means you have to cross the z minus d to the minus. And in physics, this is called a Ward identity. So just what it is. So it's just z minus d inverse. That's a propagator, which is this little line down there. Then I multiply with a. And if I do that before and I compare, it's precisely happening that it's at the cost of this additional term. So you have two propagators and this vertex sitting there. And this is what is used a lot in actually, in this case, quantum electrodynamics to show renormalizability. That's not the topic today, but this line here, which you can just check by looking at it, that's the reason for this additional term. It's very kind of basic kind of ingredients.
Go too fast. This is crucial.
So this,
So I mean, the weekly line is for dot for gauge field, and what about the dotted lines?
So the dotted line suggests that, first of all, they are not propagating yet. So these A and DA.
Yeah,
So these weakly lines are not propagating. It's the propagator of the fermion that is there.
sure.
So that's what it represents. The dotted line means I kind of insert an algebra element. There's multiplication.
And you mean the weekly line is really the gauge field that you
Yeah, so this
insert.
weakly line would eventually become also a propagating.
Yeah,
Okay. But that's only in the final. But for now, it's just kind of these lines that I draw like vertically. They will be inserting these elements, multiplying with them.
and
That's
why?
what it
What is the corresponding word identity? In ordinary sense, when you say it's a word identity.
This is usually what writes as a word identity. It's like, in fact, what happens with A is you insert momenta. So usually the word identity is something like you have a propagator for a fermion
Sure.
at momentum P.
Yeah.
You compare it to what happens with momentum P plus Q.
Yeah.
And you realize that it's two propagators
Yes.
where there's this this Q kind of
Right.
derived actually
Understand.
inserting.
I understand. So this is a translation to word identity.
So if you would write, for instance, this line here in Fourier, then it's exactly what But the main point is these 1 and 2, they're kind of the ingredients for all of the rest, and everything else will actually derive from that. All right, so one is okay. Let's see what.
So I'm sorry to come back to I'm banging away at this point constantly. So initially V was self-adjoint. And so all the VNs kind of implicitly were self-adjoint, but now we're going to allow non-self-adjoint ones. I see.
Well, I'm just trying to understand the structure of the
Yes.
brackets.
But for example, A times the self-adjoint thing is no longer.
Sure. So V's are not self-joint here.
Oh, in general, they're not.
Yeah, I'm trying to. So there's two things. I'm trying to
Okay.
analyze these brackets
Okay.
and then see what the structure is of them, and then see what I actually have to put in to get my spectral action. So it's very good that you asked this because it's kind of two separate stories. So in fact, let me focus first on that. So let me just analyze what these brackets amount to, what they look like, and how they indeed give cyclic cocycles. And for that, so I use this bracket in this way, and that's definitely not self-adjoint. So it's completely right. That's not what I have in mind. So I put in these brackets, these forms A0, DA1, and DA2 up to DAN, and I write it as a sort of a. I let it define a cochain phi n, which is like, well, why can I do this? I mean, I'm integrating a universal differential form with respect to this phi n, because I know that these A1s and A2s, if they're scalars, then the thing will vanish anyway. So I have this kind of normalized property. So I can write it in this form in terms of this universal counter. So if I look at this, then the first thing you find is that if you look at the B0 on this phi n, so B0 just means inserting a 1 okay, in the first place and nothing else. And if you do cyclic permutations of that, you just look at the formula and you see, well, there's just DA0, DA1. So there's nothing really happening. So you get all the same terms, and you just have to figure out if there's a minus sign or not. Well, for the odd ones, there is not. So you get n times B0 phi n, but for the even ones, it just vanishes. So capital B of this phi n in the even case is 0.
Cochains are normalized, so B0 is really only insertion of one.
Exactly, as I said, right? It's one in the
Sorry.
first place.
Then
Then,
you have to say.
and then you kind of do the, that's why, I mean, it's. The small b has this other property that actually an odd one will move to an even one. And this implies immediately that the even ones are Hochschild cocycles. But let's look at a case just to understand how this works, because that's already quite illustrative. So, and this is just the usual computation, but I would like to stress where this kind of ward identity comes in, or this property 2. So this is just a computation of why b of phi 1 would be phi 2. So you just look at the formula and you plug in the definition of small b. And then going to the second line, so you use Leibniz rule for this derivation of the commutator with d. And then you see that actually that expression on the second line is of the form that you have an A2 and you have to kind of cross it over the comma if you or over the bracket. And this you can do at the cost of this additional. So that's why you have A0, DA1, DA2 appearing, which is precisely phi 2 on this A0, A1, and A2. So that's why that works. And of course, this works more generally. That's not too complicated to change. Another property, which is crucial, is that if you take this b of b0 of phi 2k, then it's kind of proportional to itself. It's 2 phi 2k minus a term which is just a sort of a b0 of the second term. So this I will skip actually. So, the proof of that is similar. You just use the same properties again and again, just his identity 2. And this motivates to define psi in the odd cases, where you kind of subtract 1/2 this b0 phi 2k, because then indeed you have the property that you would like, with capital B of psi. In the odd case will be the small b kind of the next one,
So
up to a term which I just normalized. So that's actually a more, I say that's a cyclic cocycle in the sense in the odd case. So here that's the same thing again. So I just wrote the same formula. Psi defined like this. Then the kind of the conclusion from the previous slide is that these even phi 2k's they define actually Hochschild cocycles. They're also BB closed. And this other one, if you normalize it suitably, then you find an odd BB cocycle.
Just quick question. But these phi's and psi's are not defined if k is too small, because you don't necessarily have trace class then. You had the resolvent.
Oh, no,
and
but
the resolvent isn't a trace class operator.
no,
so
but the whole thing altogether. I mean, f is still around.
F.
This function f.
Oh, was
I'm
it?
not taking-
That was at the start, was it?
No, but it's
Oh.
always a trace of all these resolvents indeed. But f prime of z is in front. I mean,
F
all these
prime of
expressions
Z.
make sense.
F prime of z is just a function. How
Yeah,
can
but
that
it's controlling my summability. So I first do this contour integration and then the trace. That's actually what-
right. Okay. Oh, yes. Okay.
And of course, that's why this formula is only suggestive, and one has to do this with multiple operators.
Okay.
But all of them are.
First you do good, I'm sorry.
I integrate this trace and the contour.
Yeah. You did the contour integral before. Okay.
I think that's what I would have wrote.
Yes, it is. Yes.
And then it makes sense.
I see. So for all vi, this is trace class operator.
Yeah. Well, bounded and there's a few
Yeah,
conditions.
it's
on the-
For all of that form.
Yeah, for them.
A D bracket.
All of them, that's fine.
Yeah, yeah.
And this it gets better if you do this using multiple operator intervals. Yeah, for instance, then it's obviously. And one can do a little bit better, of course, but. Okay, so let's so we have this property now. So we have these kind of identified from the brackets, these cyclic cocycles. So let's look at how they actually enter in spectral action.
Just one question. Is it an entire cocycle?
This will also come back. And well, we're safe, so. But I need to kind of specify the function f. Okay. in what class it is. So this perturbative expansion of this is actually involved these brackets of V, which is now self-joined. So V with itself. And so we know something about these phi n's, but let's see what we get if we look at the first few terms. So I look at n is equal to 1. Okay, that's not very exciting. It's just the bracket of V. So that's just this expression over there. And this is by definition what phi 1 does on A as a universal one form. So that's not too surprising. That n is equal to 2 case is already more interesting, because there you have like V, V, and there are sums over J and J prime. And so what I do is I apply this identity 2, moving over the comma, if you wish, and then you have J prime there. Then I have an additional one form being created. And this is kind of the game one starts to play, because the first term will be phi 2 used to integrate A2, and the second one will be phi 3 to integrate A delta A, so there's a differential entering, because of this fact that I created this additional term. So this actually continues. So of course there will always be this kind of a squared, a to the third, a to the fourth, but there's these additional terms, and they're kind of accumulating more and more complicated. So this is what we structured by first looking at the first few cases, of course, but then we see, okay, now we have to develop some device to structure that. But that's not, I mean, it's still the same kind of 2 rules applied. It's cyclic permutations, and you have this additional word kind of. So, so let's see how one actually kind of re-expresses this. So going back one slide, this kind of sort of messy expressions. It's kind of hard to make sense of what you get here. But what I will do is I have this nice candidate for psi. So what I will do is I replace all the phi 3, phi 5, all the odd phi's. I will just replace them by the psi's and see what happens. This is kind of, and so this is what they amount to on the level of the integration, because the B0 I used to correct from phi to psi is of course nothing but the delta on the level of the universal forms. So for the first 2 terms, you find this. So you have this phi 1. Replace it by psi 1, so that's okay, it's the same thing. And then what you have to add is this phi 2 integral of delta A. So what happens here is that you have the psi 1 integrating A, and then you have phi 2 integrating the curvature, and this is delta A plus A squared. So the second term is slightly more complicated. There's much more identities that you need actually to make this work. But they're all based on these 2 properties, 1 and 2. The only ingredients are these 2 rules essentially to compute. And you need nothing more, actually nothing of analysis to compute this, these kind of expressions, because I use these 2 properties in a sort of an algebraic fashion. So phi 3 replaced by psi 3, and you kind of gather what you just find, and here you can actually see what happens, because you have A delta A plus A to the third. That's a kind of a Chern-Simons form. And then the additional term that you kind of collect by changing this phi to psi is exactly the curvature squared. And this continues. So this is something that actually continues on, and then of course one needs to control the kind of that kind of expansion. I need an assumption, but it's a technical assumption. It's not so inspiring to actually try to understand what this means. It means there's sufficiently full of conditions on F.
So last slide, this differential of Chern-Simons must be related to F squared term.
No, because it's not. So usually this kind of digression is. So what you do is you have a trace at the level of the algebra.
Transgression.
So
It doesn't hold here?
No, because I take this as forms. In fact, I will show you the definition. So this is something one can try to understand, but it's not completely necessary. It's just about convergence that you need. So at the right-hand side, you find these Chern-Simons forms, which are called CS, plus these additional kind of F to the K. So there are the Young-Mills or higher Young-Mills terms, which appear in even degree. Now, the notation is still the same. F is delta A plus A squared, but the Chern-Simons forms are defined like that. So there's no trace at the level of the algebra or something. There's no assumption on a trace there. And that's what you usually do there, like Quillen does, where you kind of take the transgression to get the Chern characters. So that's not the case. And in fact, these second terms here are not so much of that type, but maybe there is some connection, and we're trying to understand this, for instance, on the manifold case. But right now, this is just the usual kind of definition of Chern-Simons forms in the universal calculus. You find them as integrants for these.
That's pretty good. This is a kind of fundamental result.
Yeah, so it's very surprising. Well, also, I mean, it's just this. So it's there's nothing, no more complicated terms.
Right.
So that's very nice kind of expression, and it's under these assumptions on F, which have to do with this fall of conditions. It's actually absolutely convergent. So it's just if you want less on F, you need more assumptions on V. So you can do a little bit between them, but that's
What you mean? It fits exactly with the formula for the higher Chern-Simons.
yeah. So they will be just appearing here.
Alan,
Yeah,
this fits very well with our contractual note.
I know.
Share character, I mean, because it's really secondary.
Yeah. But, and it's also the direct generalization of the stuff with Ali.
Sure.
Yeah.
That's just
That's the starting point.
So this somehow maybe is more relevant to an earlier slide, but I'm a bit puzzled by this formula because in the classical theory of Chern-Simons, it is gauge invariant for small gauge transformations, but if you do a large gauge transformation, it'll shift by a constant.
Yeah.
And the left side here is gauge invariant,
Yeah.
but
So
according to my logic,
exactly,
the right side isn't.
no, but it actually it's not like an integral of a Chern-Simons differential form,
Yes.
but it's much more kind of it tells me much more about psi. And in fact, it tells me that psi pairing with the unitary will be 0.
Yeah.
And that would usually be the index that you're looking for. But I will come to that in a moment, because that's very interesting to see, because left-hand side is gauge invariant, right-hand side, at least it's Young-Mills, is rather.
Yeah.
So let's do that.
Do you want to use this for f and exponential or?
E to the minus x squared, yeah. That one. But we maybe like a little bit more flexibility. So as I was just saying, so you have this property that this higher f, so f would transform as u f u star, so f to the k similarly, and you find that because they're Hochschild cocycles, this will actually be gauge invariant every term. Each individual term will be gauge invariant. I also know that the left-hand side, as it's spectral, is a gauge invariant. So this means this whole series expansion is gauge invariant, which is also something that you found.
Yes, but what about individual terms?
Yeah, so there will not be. I mean, it's not like, because, so if you look at what happens, you find that there's a term appearing. It's much more complicated.
Wow.
To actually compute it. So that's not the way to go. But you have this expression following from these two properties. So the left-hand side is gauge invariant, the right-hand side. Okay.
So just what is the nature of it? You pair the phis and the psis, they form a cocycle, yeah?
Yeah.
Oh, the psi by itself.
The psi, yes, but
The psi by itself is a cocycle.
The psis, okay.
By itself, not by itself, but it's all. But the other one is just Hochschild each level.
yeah, but this also capital B is over
And
0.
you pair it not with a cycle, but with a
Precisely.
shape.
Exactly, yeah. So I'm not saying that this is a pairing between cyclic cocycles and cyclic cycles, but it's some form.
For Chern-Simons, it is.
I don't think so. I only now, I mean, so if I would take, because there's this capital A, but if I put A equals to 0, that's also already something we can look at here. So the right-hand side will be 0, and the left-hand side only has this U delta U star. Now that's then you
That's
compare.
very, I see. Okay.
Because the psi's, remember, I mean,
Sorry, yeah, sure.
so the psi's still need to be normalized to be cyclic cocycles. So that's one thing. And what you find is that the sum on the left-hand side, when I put capital A equal to 0, then this Chern-Simons of U delta U star is exactly the formula you find in the pairing with the right coefficient. So that's also what I want here. But for that, first one needs to make sure that actually that pairing makes sense or is trivial. So under the same assumptions on this F being of dk, you find that this is an entire cocycle.
So it's an entire.
And for that one needs a little bit of bounds using these multiple operator integrals in this case. So, but then one quickly arrives at that result that under the assumptions for f, which imply these condition, these bound estimates on that expression, you find that these cyclic cocycles actually entire. The main point is the second line. That's also easier to follow. Is that if you look at the pairing, that's just the left-hand side of the expression with a equals to 0 on the previous slide. Then it's precisely the pairing of u with psi.
What happens? I mean, I presume that the class of the odd entire cocycle doesn't change when you change the function. I mean, that's a question. Huh?
That's it. Yeah, sure.
I think it's an important question.
Yeah, no, I
because-
know. So what we're for instance investigating now is just to understand this form of this
I understand, but I mean, you know, it's natural to ask what happens.
zero
when-
function.
Get something different.
Yeah, and so in general, it will not be the same. So that's clear. But you're talking about something like maybe clearly if you take some kind of deformation. It should
Yeah. So what does it depend on the function? It has to depend on homological
Yeah.
input from the function.
That's a very good question. Okay.
Well, my reason to ask is that we have a specific function, the entropy vector.
Yeah, sure.
And even if it doesn't satisfy the condition, one would have to know in which class it is. You see what I mean?
Yeah, sure. No, that's a good point. One is to kind of so one of the things that, for instance, to understand these cyclic cocycles right now, or even these off-field cocycles, is to look at what happens on a manifold. So that's the first task, to really kind of understand a little bit better. Because so somehow what we're doing is we have this cyclic structure, but it's integrating some universal form, which is not, it's just a cochain essentially, a chain, sorry. And so it would be nice to understand what kind of forms, differential forms, would correspond to the, for instance, these whole-field cocycles in the sense of this discussion of yesterday, for instance, Hochschild, Constant, Rosenberg, then in the smooth case. Okay, so let's see. So I have a few slides, a few final thoughts on loop corrections that may kind of be of interest. So you ask for it, so and the rest have to suffer. and
We have to take our revenge.
yeah. But it doesn't. But now just a few minutes. But it's
not over.
Some homotopy groups.
Yes.
Does this compute index somehow? I mean, index of original.
No, but this is what it told you. It tells you that the pairing is trivial with K1.
yeah, but it's not so clear what if it's an index of D related to U and so on. I mean, what is the actual index?
Okay.
But that's why I would like to understand better this psi. Okay, so loop correction. So this is about quantum fields, because I was saying I could derive some action functional like Einstein Hilbert physical Lagrangians, but they're classical. So there's like it's like classical equations of motions, whereas we know that we should be doing something more quantum, so quantum physics. And what I would like to use is this kind of this Taylor expansion as a sort of a starting point of a quantum, what a classical kind of prescription for a quantum theory. And the usual way, in fact, in this case, it's very similar. It's because I work with these this context of Hilbert spaces and D and these perturbations. It's very natural to consider them as sort of a matrix model. So you have like it's infinite dimensional, so it's on H. So one has to be somewhat more careful. But it's very natural to actually attack it from that point of view. First of all, because there's no locality. So if you would do so quantum field theory as usual is something on a manifold, but this is kind of completely in the data. So there's no way to kind of identify some manifold structure. In fact, this is completely general. So any spectral triple will work. So, so this I would like to compute. And so this is called a partition function. There's some weight, an exponential minus trace. That's my spectral action. And what I do is I use V has what is called the background field. And I kind of take that as a starting point, so D plus V. And Q is the field, the quantum field that I'm trying to integrate out. And this is kind of the quantum degrees of freedom that one's trying to integrate over to see what you end up with in a sort of an effective theory, which is this left-hand side.
So you mean, Walter, here you are looking at the gauge path. You are doing the functional integral on the gauge
On
path,
the gauge part. only.
not
Yes.
D of D,
No.
which is
That's
ultimately what you want to do.
one theory, challenge. So it's only the gauge sector that I'm trying to, also because I looked at this perturbation in V.
Yeah,
That's
sure,
the thing.
sure.
Okay, so let me try to compute this, and this is usually done by first of all making it well defined. That's always a good thing, even though in physics that's maybe less of importance to make sense of this this integral. But this partition function can actually be well defined by restricting to finite size matrices, Hermitian matrices, and that I do in the basis, the eigenbasis of D. This is also given to us, it's kind of the background. And the eigenvalues are these lambda k's. Then the quadratic form, it has a very nice expression, which is that type, q k l q k prime lambda k lambda l. And the more generally, I have these expressions where it's like a trace, but there's a form factor which comes from divided differences. Like here on the bottom. And so maybe I should say that, so we had a discussion just before COVID in 2019, when I was visiting in Sydney, with the supership. We were trying to kind of propose how can one make sense of these formulas and maybe drive this as a quantum theory. So then at that point, so Teun was also there. But of course, we both traveled from Nijmegen and we had these discussions. We learned a lot. Coming back, we could actually use these multiple operator integrals at that time. So that in that sense, so we didn't solve this problem in Sydney, but we took this kind of techniques and it really helped to kind of bring this to a good end. So that's so one of these things is this Gaussian integration of that type. So I have this kind of only this -1/2 QQ, which is this single term in this this partition function. Then if you integrate this, then these are just kind of integrals one can actually do, and one finds that one has to invert this divided difference, usually. But it actually works here as well. And that would work for a suitable collection of functions. So one has to be a little bit careful that should be positive, this f prime. That's not a very natural condition, so there's some tension here between the truncation, the finite size truncation, and this function f. But I think I consider this as a regulator. So what it amounts to is that besides these arrows, which I was drawing for fermion propagators, which is like corresponding to resolvents of D, I first of all, I consider these kind of blobs as vertices for my diagram that is built with these kind of these wiggly lines. And the wiggly lines themselves also propagate, and they have a propagator, so they are attributed to this kind of inverse of f prime, just like we had the inverse of D for the other lines. And these are the divided differences that are kind of assigned to each of these vertices. And I draw little blobs because it's important that there's sort of there's only cyclic permutations that you can do on this vertex. But I cannot just kind of, it's not like with a graph where you can just kind of change the order of two of the incoming edges. But that makes it actually more of a ribbon graph or a fat graph than an ordinary graph. So this is what we did. The task is then to kind of accumulate all of these diagrams and assign every time this following these two rules, these things to each graph, and then sum that. And then pictorially, it looks like that. There's some assumptions on what kind of diagrams, but that's not so relevant here. And I just tried to compute this double bracket now, which should be kind of the quantum replacement for the single bracket, which is the classical action. And now there is this really surprising property, is that there is a sort of a Ward identity also for this boson propagator. So there is this idea that if you, it's in the same way. So I have this propagator, then I add something after and before I look at the difference, I find that they create a new vertex. So I have this additional vertex created in exactly the same way as I had for these fermion propagators. And it's just a consequence of this identity, which is about divided differences in the way you define them. So it's nothing very spectacular, but it's just there at the diagrammatic level, which makes it very suitable for kind of trying to get to a what identity on this double bracket. Because that's what it kind of drives. So this kind of pictorial identity allows me to show that if I do this for the double brackets, and this I do at one loop, that's just the status where we are. And I look at suitable kind of potentially divergent or relevant diagrams. And I find that this difference by moving over the comma again is just at the cost of this D commutative with A. And this is called 2 prime. And here's some examples that one can look at. So these are like 2-point diagrams that one has. Here are the 3-point diagrams at one loop. Maybe it looks like I have more loops, but remember that these kind of, I only count the loops for the wiggly line. The other things, the blobs are just vertices. So it could be actually much more improved in terms of ribbon graphs. But so what I have to do is to take it kind of the first entry there and assign these kind of these entries A, which is what I did here. It's just to kind of convince you that these things work. Is that I insert these A's at several places. So before the V1 and after the V2, look at the difference. I collect some diagrams using this property of generating new vertices. If I take into account all of the diagrams that I have at the 2-point level, I generate all of the diagrams that I have at the 3-point. So that really works, and this works for endpoint diagrams at one loop. That's where we are at this moment. So that's proving this little equality over there. What it tells me is the following. So I have the same algebraic relations at this quantum, this one loop quantum level. So this double bracket, it satisfies 1 and 2 prime, but it's just the same thing. So it means I can do the whole talk again.
Amazing.
So let me just summarize that. and I get cyclic cocycles. Psi, I call them psi tilde, phi tilde, but that's a typo. They should be called psi 1L and phi 1L, so at one loop. And I don't know what they are, but they're expressed in terms of my my spectral input. So that's already very good. And they're just some cyclic cocycles for the same reasons. And it means that if I want to kind of absorb these terms in the kind of the classical level by subtracting them, so to make sure that the theory is well defined, I'm just looking at some kind of transformation between these cyclic cocycles. So I have to subtract something, but they're all cyclic cocycles. So I just have to kind of look at how to move in my cyclic from my cyclic cocycles to make the theory well defined. So that's kind of the first kind of sign of what we're seeing, is that you have to kind of change the cyclic cocycles in order for the theory to be well defined at higher loop level. So that's something that we're kind of investigating at the moment, of course, to move beyond the one loop. All right. So with that, I would like also to gauge again the talks to 1 hour. So thanks for your attention.
All right. So yeah, how far are you from getting the quantum corrections to the geometry, which should be the dressing of the propagator of the Dirac plane?
No, but this is.
I know. I understand that. Okay, this is another piece of the story.
Yeah, this is the bosonic sector.
This is the bosonic sector. But okay, what one would opt for is that you can sort of react back and begin to see the quantum corrections to the geometry.
Sure. So in principle, as you see from the diagrams, one could also draw like fermion propagators.
Right.
But one has to take them into account. So you have the same.
Exactly. So this is because then, okay, I mean, one would have really the hopes that, and also what should then combine that with the understanding of the cosmic Galois movement. I mean, because this is like the first piece of the renormalization.
Oh, sure. I mean, this is that's what you see here, and it's nice that it kind of stays So the first thing is that maybe, so what we used to do in these applications to particle physics is take this Lagrangian, but then take this as a starting point, take a physics textbook, or I mean, know the physics, and then do the RG flow there, but then you lose the contact with the spectral approach,
Exactly.
because you just look at the Lagrangian on the space. And in fact, you lose the spectral property.
Sure.
But here, everything, what one finds is still spectral. So all these brackets are defined using only the spectrum, only the operators.
It's a fantastic step.
It doesn't mean one can compute this
No,
and
okay.
compare it to,
Forget it.
but if one could connect this, for instance, to the computations that we used to do, then that's sufficient.
It means you can extract much more information from the spectral data. Spectral sequence. Because we extracted the chain character. The refinement.
But I mean, the chain character was kind of cohomological.
Yes.
And here it's much
Right.
more because
But it's also from spectral data.
it's also from spectral data.
Yeah.
But what it suggests, if you want, is that eventually the renormalization group and all that, they will just act at that level and they will renormalize the geometry, which physically makes a lot of sense because, I mean, of course, when you do physical measurements, you cannot ignore the quantum corrections. So that's one thing that we have been thinking about with Walter. What does it mean? I mean, when you think about, for instance, what they call quantum gravity, doesn't make much sense to transform the G mu's in some series, but it makes perfect sense to dress the Dirac propagation. And this is the dressing of the geometry.
So there are several places in mathematics and physics where you add a 3-form to the Dirac operator, I guess mainly as a background, although I suppose it gauge transforms. I don't know. So I'm just wanted to throw out the idea that maybe putting a 3-form into the formalism.
Oh, you mean this is what string theories do?
For example, Constant also had the Dirac operator on a compact Lie group and added the standard Clifford multiplication by the 3-form. And it also occurs in 11-dimensional supergravity in work of Greg Moore.
Yeah, in a way, it's just John Simons is playing that role.
Yeah, because I would rather actually maybe change D to capture this. So
That's what I'm
that's a
saying.
1-form using D, a 1-form, but it captures this 3-form property that you're looking for.
Well, I would like to see that in action.
Yeah, I mean, this,
Yeah.
it's just a guess because, for instance, I mean, the scalar field, which is not really a 1-form, if you think about it classically, it's actually a 1-form in this sense. It's in omega 1 D. So there's a kind of much more potential to put kind of perturbations in this kind of
I
differential.
would suggest
That's what Fasten did.
But I would suggest a good test case would be to try
Sure, yeah.
taking Constant's Dirac operator
Mhm.
Yeah,
and run
yes,
it.
it's a perturbation
Yeah.
by a 3-form.
So a naive question, if I may, you didn't mention Feynman integrals, but are there any connections?
I did mention Feynman diagram. I think
you
there's
did?
Feynman at some point.
Sure.
Okay.
Fine,
No, of course. I mean, this is,
Okay, what's the connection then more precisely?
well, it's so it's not like a Feynman integral in this sense, but what I'm trying to compute is like a Feynman path.
I think you had the slide on the Feynman integral.
I think it's two word here.
No, even before.
No, no.
You had the
Okay.
functional integral.
This functional integral is in the same sense, but not with an I. So that partition function is like a Feynman path integral. Except it's in a Euclidean signature. Yeah, but it's completely this idea.
So I mean, is it like just a formal expression or?
This is, so I make it well defined by regularizing Q to be finite size.
Because for finding the spectral triples, you can really work with DD in that case. And you get really very quick connections to random matrix models and you get expansion.
But I want to
Why
see that
don't you
works.
cut it off and then you take the limit?
Because I mean, it's function plus F. And it's completely opposite, so it's polynomial
Yeah,
in
yeah,
this
of
case.
course.
And this is, I'd like them to be.
But I mean, also in the path integral approach, there's no F. It's just a polynomial, like to take Landau Ginzburg, for example.
I want to, I mean, this is a kind of a arbitrary trace of F of D. And if you want, you can take it
Yeah,
the way you
It's
would
kind
like.
of normal, renormalizes.
No, but it's just a special case. I mean, I take trace of f of d. If you take f to be polynomial, then you have that model. And then you could maybe integrate all of it.
Yeah,
I would
but
like
in that case, F cannot be just
No, sure.
rapidly function. It has to
No,
be
that's the limitation of that approach, right?
Yeah, yeah. Okay.
Are there any other questions from the audience? Any questions from Zoom? Okay, let's thank Walter once again.